So we're going to go over the 5b through 5c FIP. As always, if you missed it, I just exempt you, and you take it on your own for your own purposes, for your own benefit. So this is kinetic energy, the 5b problems, and then work kinetic energy theorem. I still don't have a good definition for what theorem is. If Mr. Pakinowski's teaching calculus, ask him. I'd love to get a good definition. So number one, we've got this swimming beaver. The beaver swims 93.625 kilometers in 24 hours. If the mass of the beaver is 55 kilograms, what's its kinetic energy? So for kinetic energy, we know that Ke equals 1/2 mass velocity squared. That's just overall Ke. This is before we get into ideas of initial kinetic energy and final kinetic energy, change in kinetic energy. So this one's really straightforward because you're given mass and you're given the tools to find velocity, but you had to convert. And that was the number one mistake on this problem. It was really simple. I actually did it all as sort of one piece when I listed my variables. Mass is 55 kilograms. The velocity, you can do this as one step by saying, oh, well, it's 93.625 km per 24-hour period. I'll have to move this over to do this. And then if I just say, oh, well, 1 kilometer is 10 to the third meters, and 1 hour is 3,600 seconds, or 3.6 times 10 to the third seconds. What we get for velocity is 1.083622, on and on and on, meters per second. Why do you have to be in meters per second? Not just because I have because joules, if we look at the units for joules, 1 joule is 1 Newton meter, and 1 Newton is 1 kilogram meter per second squared. So if you're not in meters per second, your units don't work, and you get a nonsense answer. And that's where that dimensional analysis comes in. Okay, so then Ke equals 1/2 55 kilograms. Let me shrink this. And times the 1.08, etc., meters per second. And that's squared. That was the other mistake a few people made, and this is a really simple one. It's a classic mistake. You write out the formula, you write that the velocity is squared, but then you forget to square it. So what you get for your kinetic energy should be 32.2915, on and on and on. With sig figs, you get a Ke of 32 joules. So pretty easy. Like I said, I think all the mistakes I saw were just dumb mistakes. So that's great. You got a chance to get them out of your system. So, all right. The second one was tougher, and boy, I got caught in the same brain fart that a few of you did. We have, this stupid monkey on a sled, and like I said, I pulled this one directly from the book. It's out of the chapter review. It's one of the unassigned problems. Monkey on a sled. Monkey is pushed, and maybe I should change the wording on something like that to shoved, which indicates like you give it a shove and you're not pushing it anymore. In my mind, yeah, pushing kind of like you're thinking that you're continuing to push. You're not. You shove the monkey up the ramp and see how far it goes. So the forces on the monkey, and force of a free body diagram is tremendously helpful here. I'm drawing it very badly. Oh, we have no force that way. So we've got the normal force, of course. Normal force, of course. We have the force of kinetic friction. We have the force of gravity. And, of course, we can divide out that force of gravity into an F of gy and an f of gx. FGY is going to equal mass, gravity, cosine theta. And a word about this, I had a discussion with somebody last night at tutoring about this. Anytime you've got a slope in these problems, there's a real opportunity to mess yourself up. Because we're so accustomed to, things like dividing up gravity. Well, mass gravity, cosine theta, mass gravity, sine theta. And it's easy to think that that takes care of this, where work equals force cosine theta d. That's a different theta. So we're gonna talk more about this one. Okay, so force gravity, and I'm calling this something like cosine r, cosine of the ramp, or theta of the ramp, something like this. And of course, FGX is mass gravity sine theta, again, and that's theta of the ramp, theta of the slope that you're dealing with. So we've got all that. What we need to do is find the distance. So we're looking, whoops, that doesn't work. We're looking for this piece. Well, remember that this is the net work, so it's equal to the net force times that cosine theta times distance. And we have something else that we can set up that's also equal to net work. Net work is equal to the change in kinetic energy, the delta KE, which means it's equal to 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. Well, that gives us something we can latch on to. So let me shrink all of this. Shrink my force diagram. Shrink that. Shrink that. So what we're going to end up setting up is this. Net force times cosine theta, whoops, d equals 1/2 mass final velocity squared minus 1/2 mass initial velocity squared. Now some of that's going to simplify and go away. And we do a lot of these kind of problems with work kinetic energy theorem. Something is moving, how long does it take to stop? Like where does it stop in terms of distance? Because that's a really great use for work kinetic energy theorem. You've got work being done by friction. What distance does it take to stop? You can do braking problems with this. We're not telling the world that. Okay. Why is this easy? Because the point at which it stops, due to the work done on it by other forces, is the point at which final velocity goes to 0. So that becomes 0. So we've just simplified it a little bit. So now we have, the net force times cosine theta d now equals the negative of 1/2 m initial velocity squared. And we have an initial velocity, we have a mass. The net force is within our grasp. We aren't given it, but we're given the means to work it out. And while this probably, again, will cause flashbacks to Chapter 4, it's not as bad as that. If we want to look at the net force, we know it exists on the x-axis, with our standard tilted axis set up. And so if we do a sum of forces on the x-axis, we know that it's equal to ma, which we don't care about, but we know that that's going to be the net force, and the only forces acting on the x-axis because the pusher is not continuing to push. They shoved and let go. So the only forces you've got are F of gx, which is acting downhill, and F of kinetic friction, also acting downhill. So F of gx is easy to find. we have mg sine theta of the ramp. We're given the coefficient of kinetic friction. So we have to go back and do a little sum of forces on the y for ourselves. And we know that normal force and F of gy are the only two things there. So we know that normal force is equal to the negative of F of gy. And we know that mu k equals Fk Fn. So mu k Fn equals Fk. And we now have the means to solve for Fn, because it's just the opposite of force of gravity on the y. And one mistake I saw people make on that was making normal force opposite the entire force of gravity, just forgetting, and that's a chapter 4 thing, you've done it a lot, but it's also easy to forget. You know, you can't let all your skills rust. So, do you want me to go through the entire solution for, or do you want me to just give you the number for net force? Is that okay if I just give you the number, or do you want to see? Okay, so what we end up, well, here, mu k, I'll put in times negative FGY. Okay, so that's our net force, and the raw net force that we get, shoot, I don't have it on here. It's 118.4 something, is that correct? Yeah. Okay. And of course that's newtons. So we now have net force, we now have mass, we have initial velocity. We're solving for distance, and now let's talk about that darned cosine theta. So this is one of the prime opportunities to screw something up. When we're looking at this, F net cosine theta d equals work net. This theta is the theta between the force that's doing the moving, or the force that's acting on the plane that's doing the moving, and the movement. So it is very literally the theta between the force and the distance. And hey, look at that. It's theta between force and distance. So the equation tells you what it is, which I didn't see until this year. Oh, hey, look at that. You know, so even if you had to figure your force on the x-axis using, you know, mass gravity sine theta, that's your theta with your ramp or your hill or whatever. The cosine of theta that we're looking for here, we're talking about the theta that exists between the force doing the motion, doing the moving, or doing the work on the object, and the object's motion. So in this case, because we're talking about friction and gravity, and friction and gravity are operating downslope or upslope? Downslope, both of them. Which way is the object moving? Upslope. So what is this theta? 180. So basically, it's kind of going to always be 180 or 0, I think. I hate, you know how nervous I am making like it's always kind of statements, but I can't see a case where it wouldn't be 180 or 0. And what that's going to give you is either a 1 or a negative 1. So, you know, this is assuming that you've already gone through and figured out which portion of the force is acting on that axis. So, okay. With that, we're now ready to solve for distance. Whoa, that's not what I wanted to do. So if we solve for distance, we have, let's tuck that up there, we have distance is equal to negative, well, and we can do the math, the algebra, mvi squared over 2 f net cosine theta, where that theta is 180. What we get for a distance is something like 1.35 something something. So with sig figs, we end up with a 1.4 meters. Okay. Simple mistakes. Lots of people made really simple mistakes. Or got stuck in the same brain fart that I did, where I'm thinking, well, what's the force of the pusher? Once it's no longer in contact, it's not exerting a force. So, questions, comments, concerns? Yes, sir?
I didn't use cosine in my problem.
Okay.
I figured the force was negative because it was going down.
And you can do that. You can do that. I'm not a stickler for saying, no, you must use F cosine theta d. It's perfectly valid, I think. When you get to college, a physics instructor may feel differently about this, especially for the work problems. I think it's perfectly valid to say, okay, the force is operating in the opposite direction of the motion, it's going to be negative work, or the force is operating in the direction of the motion, it's going to be positive work. So I think that's reasonable. Like I said, your first physics prof may beat you over the head with a physics stick for it. I don't know. Don't come crying to me if they do. So, questions, comments, concerns other than that? That was a good one. Okay, I will address questions on homework. Okay, so on 5C, this is your basic setup. You have this thing being pulled up a ramp, and we're given the mass of the crate. We're told that there's the puller, somebody's pulling it up with 100 newtons of force, and we've got a coefficient of friction, mu k of 0.40, and we have a ramp angle of 15 degrees. Great. So what we're asked for, there are basically three forces that are doing work on this object. There's the force exerted by the puller doing work on the object. There's the force exerted by gravity doing work on the object. And there's the force exerted by friction doing work on the object. So this is very much like the problems where you have 5 people pushing on one thing and you have to find net force. You're finding the work done by each of those things, and then you have to put it all together to find the net work. So to do that, the easiest thing to do, honestly, is to redraw your picture and separate it out so you only see the force that you're concerned with. So for part A, we're asked about gravity. Perfectly valid to redraw this with nothing but gravity and look at f of gx and think about what work that's doing. Okay? So the work done by gravity is going to be equal to the force of gravity on the x, cosine theta, which is the theta between the work being done and the motion of the object, which is 180. And we know that this is mg sine theta of the ramp. Does that make sense? Okay. And I think we did that one yesterday. So that one is easy, and you can do a picture that only shows gravity. Now for part B, you can't quite get away with that as cleanly, because for part B, we're talking about the force of kinetic friction. And the problem is that to find the force of kinetic friction, since it's not given to you, you're given the coefficient, you have to use mu k Fn equals Fk. Which means, of course, to find Fn, you got to deal with f of gy. So we can do the sum of forces to prove to ourselves that Fn equals f of gy. So negative f of gy equals Fn. So mass gravity cosine theta of the ramp equals Fn. So the force of kinetic friction is 0.4 times mass gravity cosine of the ramp. Oh, I'm sorry, yeah, negative of. So that gives you your force of kinetic friction. And let me shrink a bunch of this junk. What that means is that the work done by kinetic friction is equal to the force of kinetic friction cosine theta d. Okay, So you get the work that way. And the polar is easy because it's given to you. Work of the polar is equal to the force of the polar times cosine theta. In that case, the theta for that is 0 because they're in the same direction. And you have the distance that it moves. So C work of the polar equals force of the polar cosine theta d. So are we good? Okay, so now let's look at part 5D in problem 5 in section 5C. Holy moly. So this asks for the net work, and there are two ways to do that. One is you can find the net force, and you know how to do net force in your sleep at this point. Hey, it's all going to be on the x-axis. Sum of forces on the x is going to equal net force, and I've got force of the polar up the ramp plus force of gravity down the ramp plus force of kinetic friction down the ramp. I have my net force. Net work equals net force cosine theta d. And the theta here, the net force, is obviously up the ramp because the object is still moving up the ramp. If the net force was down the ramp, the object would be moving down the ramp. So that's one pretty clean way to approach it. There's a sneaky, tricky, rotten, dirty shortcut, which is that just like net force is the sum of all the forces, net work is the sum of all the work, which is a really easy way to do it because you just figured out the three things that are doing work on this object. Now you may have a difference in terms of sig figs, even if you're careful, but you can literally add up all the works and get the net work, which is stupidly easy. Now, it's nice the way this problem is set up because you have to do part A, part B, part C, and then you have part D, and you can add them all up. What would be really mean is, just giving you the setup and then taking you straight to part D, having not figured out the work done on each of them. And then then you would just do the net force probably and go from net force. But if you've already gotten all the sections, all the pieces of the work, gee, it's easy to add those. So once you get that net work, they ask you what the speed of the crate is. And this is where this becomes a work kinetic energy theorem problem. I just lost the top of my F. There. So on 5E, because what we know is that the net work, whatever you got in the last part in 5D, is equal to 1/2 mass velocity final squared minus 1/2 mass velocity initial squared. And you have an initial velocity, you have a mass, you now have the net work. All you have to do is solve for final velocity. So, fairly straightforward. Other questions? Like I said, I keep saying it, so I think you'll probably pay attention. I always put one like this on the test. Pretty much a guarantee. So why don't you just staple the homeworks, put them in the box, we won't trade and grade, and then we can start to talk a little bit about potential energy.